All right, welcome back. I hope you're having an amazing time so far. Our next speaker is Tyler McKean. He is Head of Customer Success at Superb AI. Please join me in welcoming Tyler to our virtual stage.
All right. Hello, everyone, and welcome to our discussion on how to build efficient active learning flows with the Superb AI suite. So before we begin, I'd like to quickly introduce myself. My name is Tyler McKean, and a quick background on me is I studied economics and computer science during my time at university and took some courses in machine learning. Since then, I have worked professionally as a software engineer, a senior technical consultant, and am now the head of customer success for Superb AI. So as a quick agenda for today, we're going to discuss a brief overview of who Superb AI is and what we do. Next, we will answer the question, what is active learning? Third, I'll provide a summary, how to leverage the Superb AI suite in conjunction with an active learning workflow. Fourth, I'll discuss a real-world example in which active learning was applied and successful. And finally, we'll open up the floor for some questions and answers. All right, so first I'd like to begin with a quick overview of Superb AI, the platform for data management, labeling, and operations. So Superb AI Suite is a data labeling platform that allows product leaders, machine learning engineers, and anyone else to scale up quickly and effectively by providing computer vision data management and labeling capabilities. The suite offers a host of features from annotation and user analytics to a robust manual QA workflow, as well as direct integration with cloud providers and a robust CLI and Python SDK. Our custom auto label or CAL product combines the best of both manual and automatic labeling techniques. As the name suggests, the CAL leverages subject matter expertise from manual labeling and advanced machine learning techniques to distill such expertise into an automated solution. Auto label technology is built on a handful of machine learning paradigms, including transfer learning, few-shot learning, supervised learning, and also leverages other machine learning techniques to assist with uncertainty estimation and active learning. Our CAL not only labels your data automatically, but also picks out the hard examples that are the most valuable for model training, thereby enabling our active learning workflow. We also have a common object AI, which is a set of about 180 object classes, which we have pre-trained and are ready out of the box for your use case. Common object AI includes things like people, animals, several types of automobiles, and many others. Lastly, we have our active learning toolkit, which allows teams to leverage our uncertainty estimation and difficulty scoring to quickly and efficiently identify high-value examples for your model. By leveraging auto label in conjunction with uncertainty estimation, machine learning teams are able to scale performance of their models more rapidly than ever. So now I'd like to dive into what exactly active learning is and the various principles that can be applied to a project. So as a basic definition, active learning is a machine learning training strategy designed to enable an algorithm to proactively identify subsets or elements of training data that may most efficiently improve performance. So what exactly does this mean? Well, machine learning teams can leverage active learning principles and feature sets to automatically uncover gaps in their training data or model's breadth. Rather than having to weigh all elements of a training data set equally, we can use active learning to identify the most valuable elements that will likely result in the model becoming more accurate, more efficiently. So here we can see a visual representation of how active learning accelerates a model's accuracy using an iterative approach. On the y-axis, we have model accuracy, and on the x-axis, we have the amount of labeled data. The white curve shows different iterations of the same model as it was trained on increasing amounts of training data. You can see that the model accuracy for the model using random selection improves somewhat linearly until it approaches its ceiling. The other curve on this graph represents a model that is trained using an active learning strategy and principles. Here we can see that the model's accuracy gains are significantly accelerated as compared to the model trained using random selection. This is because with active learning, we can actively identify examples in the training set that will be most beneficial to improving our model's accuracy on the test data. The model trained using active learning principles and tooling has a higher accuracy with the same amount of training data for pretty much the entire life cycle of the model's development. These types of accelerants when training a model are extremely valuable to teams focused on speed, cost savings, and getting to market as fast as possible. So, as mentioned in the previous slide, random sampling is a classic approach to determining training data used for continued iterations of model training. Random sampling is implemented as a strategy to learn about an entire data set or population with only a small amount of data. One of the reasons in which random sampling is so popular among data scientists is because of its simplicity. Choosing data at random requires no knowledge of the items being researched or labeled, making it incredibly easy to implement. In addition, random sampling does not involve prior classification, thus reducing the likelihood of errors. As the slide says, the idea behind this technique is to weigh each piece of data equally so that our training data is representative. So one type of active learning is what we call stream-based selective sampling. Stream-based selective sampling is a thorough and autonomous approach to active learning. It works by iterating over all elements of the training set and then using a threshold to determine whether it should fetch the ground truth answer or apply its own inference to the label. This approach is thorough, as I mentioned, but requires a high time and expense budget and can exhaust both of those very quickly. Another active learning strategy is called pool-based sampling. In pool-based sampling, the machine uses informativeness, meaning that the data contains valuable information and should be labeled. When measuring informativeness, we look at how useful the data is and determine which examples should be included in training our model. After a pool of data is selected for labeling, machine learning professionals will choose to train a portion of it, typically around 80%, and then validate the remaining 20%. In this approach, it is paramount to understand which examples yield the lowest prediction precision value, as that data will help improve performance. In other words, the images with the lowest levels of accuracy can be used to help train your model in the future. The active learner in this case is usually initially trained on a fully labeled fraction of the data, which generates the first version of the model, which is subsequently used to identify which instances would be the most beneficial to inject into the training set for the next iteration or active learning loop. So now that we have covered a handful of active learning strategies, I'd like to dive into how active learning works on the Superb AI platform. So Superb AI's core active learning technology is what we refer to as uncertainty estimation. Uncertainty estimation is an entropy-based querying strategy that selects instances within the training set based on the highest entropy levels in their predicted label distribution using our underlying uncertainty sampling. The underlying technology for the Superb AI uncertainty estimation feature set uses a patented hybrid approach of both Monte Carlo and uncertainty distribution modeling methods. We also have a published white paper on the strategies behind some of our core technologies, including uncertainty estimation, that you can feel free to download after the presentation. So our uncertainty estimation and active learning feature set aims to actively identify and label data of which the model has determined to have the highest output variance in its prediction. Another potential query strategy is to identify examples which would minimize overall output variance. This alternative strategy is known as variance reduction. So now that we have discussed some of the strategies, principles, and technologies behind active learning, I'd like to walk through a real-world example using the Superb AI suite. So the use case I'm going to talk about today is a surface defect detection task using a data set comprised of X-ray images of steel pipes. Our goal was to demonstrate that we can create an accurate custom auto-label model using a very small data set by leveraging our active learning feature set. Some preliminary details about the project are that there are a total of 7 defect types or object classes contained in the data set. These are bite edge, crack, overlap, slag inclusion, broken arc, air hole, and unfused. The data set is relatively small in size, totaling 774 images across the training, validation, and test sets. It's also worth noting that this particular task calls for bounding boxes of these object classes. So here we have some samples of the data set and the surface defect classes. As you can see, these industrial defects are relatively subtle to the human eye and require some subject matter expertise to correctly classify. One of the ways the Superb AI platform can help teams is by building a model that leverages subject matter expertise in the beginning in order to save time and expense down the line. So now that we've set up the premise for this project, I'd like to dive into the steps we took to carry it out. As a first step, we utilized random sampling to identify our validation set called Val1, which totaled 178 images. Additionally, we randomly sampled another subset of data to be our initial ground truth set called GT1. Next, we then utilized our subject matter experts to manually label both Val1 and GT1 all within the Superb AI platform. By explicitly defining a validation set up front, Superb AI knows to use it as a static validation set as you iterate on your custom auto label model, allowing you to easily track efficiency and accuracy gains over time, while also highlighting potential biases in your training data. The next step was to use our export and train features to train a custom auto label model for this use case called Cal1. Finally, we were able to see the initial results of the custom auto label model trained on GT1 and Val1. So here in this screenshot, you can see the output of precision and recall and labeling efficiency boosts for each class in the Cal. After a custom auto label is trained and deemed appropriate for use, you can apply your newly created model to your project settings and enable the auto label feature. Once the model is configured, all you have to do is select data within your label list and click the auto label button to kick off the task. Once the auto labeling is complete, each auto labeled image will have a corresponding difficulty score, as can be seen in this screenshot. This leveraged our uncertainty estimation and entropy-based querying feature set to divide each example into one of three categories: hard, medium, or easy. You can then use this difficulty score to determine which elements of your dataset are most likely to improve performance if incorporated into the next iteration of training. For the next step in this experiment, we utilized difficulty scoring produced by uncertainty estimation to define a new subset that is most likely to contain the highest degree of information usefulness for our model. We determined this to be a dataset containing 251 labels of difficulty medium and hard, and also where the model did not annotate the image. We called this dataset GT2 and then QA'd each example in order to ensure correctness before training. It is worth noting that uncertainty estimation and difficulty scoring has a very strong positive correlation with mistakes in auto label annotations, as opposed to those where the model determined the task to be easy. After this GT2 set was trained, we then added it to our training set and used Superb AI to train a second iteration of our custom auto label model, this time with our original ground truth set, GT1, validation, and the newly identified GT2 subset. This approach of active learning can be described as pool-based sampling, as we discussed earlier. So you can see on this slide that the precision and recall improved for almost every class, as well as the expected labeling efficiency boost. We can see that the object slag inclusion was the most notable increase, but many others had double-digit increases in precision or recall. Earlier in the presentation, I made the claim that active learning not only improves our model's performance with continued iteration, but also actually accelerates model improvement as opposed to a random sampling method. So as a final step to this experiment, we identified another subset of the training data, which we can call control, which is the same size as the GT2 subset identified with active learning. So finally, we can see that the Cal results on the control group are indeed higher than the first iteration of custom auto label, but that the results for the custom auto label trained using active learning, or Cal2, are even higher. Our precision or recall were higher in the majority of classes, thus showing that active learning can not only improve, but accelerate our model training and accuracy. Thank you so much for your time today, and we're looking forward to answering any questions you may have.
Wow, Tyler, that was incredible. I know the audience learned so much, and we really appreciate you taking time to share your incredible knowledge with us. The audience is giving you a huge virtual round of applause. Thank you again. And for the audience, it's time for you to make your way to your next session. Along the way, make sure you accept your connection request and take some time to check out our awesome exhibits. Thanks so much, and we'll see you around.